Thanks very much. Thank you all for coming, everyone. It's a pleasure to see you all here on the sort of dying moments before break week. So this is the third of our series of seminars on the topic of quantum materials. It's a pleasure to be able to introduce today's speaker, Professor Graeme Luke from the Department of Physics and Astronomy here at McMaster. Graeme received his bachelor's degree in engineering physics from Queen's University and then went to complete his PhD in physics at UBC. After graduation, he did an NSERC postdoctoral fellowship at Columbia University, where he continued on first as an assistant professor and then as an associate professor. So he came north of the border to join us here at McMaster in 1998. And his research interests really span a whole range of different quantum materials. In particular, he's done some really interesting and exciting work on geometrically frustrated magnetic materials, such as pyroclares, as well as unconventional superconductors. He's also an international leader in the use of muon spin resonance techniques, and he also holds an affiliated scientist position at Triumph. So Graeme is a fellow of the American Physical Society, has been a member of the Canadian Institute for Advanced Research Quantum Materials program, and currently sits on the Triumph Science Council. He also won the 2019 Brockhouse Medal from the Canadian Association of Physicists, which recognizes outstanding contributions to condensed matter and materials physics. So today, Graeme is going to be telling us about some of his recent work that combines the topics of geometric frustration and superconductivity, and talking about the search for broken symmetries in Kagome Lattice superconductors. One more piece of housekeeping just before I hand over to Graeme. Just a reminder that the seminar series will continue next week, but at a different special time. So please come back again for the last of our quantum materials talks next week at 1 p.m. And with that, I'll hand over to you, Graeme. Feel free to take it away whenever you're ready.
Great. Well, thank you very much. And thank you very much for the very nice invitation and the introduction. Looking forward to it, although we're sitting about 10 feet away from each other right now across the hallway in different closed doors. Soon, maybe we can look forward to having seminars where we're all in the same place. So let me see if I can share my screen and share that. There we go. And then let's turn this on and away we go. Okay. So I'm going to, so it's great to see you all here. And today I'm going to talk about sort of a search for broken symmetries, as Pat says, in a Kagome Lattice superconductor. So this is a sort of a topic that combines a couple of interests of mine. It's looking at interesting lattices, and the Kagome is very famous as a geometrically frustrated lattice, and also looking for sort of exotic superconducting states, which is sort of another thing that I'm very much motivates me to come into work each day doing science. So, so there's sort of two ways of thinking about science, and I sort of like there's sort of the particle physics reductionist model, where it's this, it's a standard model as an example of this, where you try and simplify things down to the simplest possible, building blocks. You break things into their constituent elements, and this works very well for understanding the fundamental particles of nature. We've got the fermions, which have the electrons, and the muons, which will come up shortly, etc. And this is a very good way of looking at the universe. It leads to the periodic table, which of course you can see down in the entranceway to ABB when you come into our building. It's a very good way of classifying things and doing studies. It doesn't always work. It's not always the most, this reductionist technique doesn't always work for really complicated systems. If we have a condensed matter system, there may be 10 to the 23rd atoms in a cubic centimeter. If you're good with solving the Schrodinger equation, you can maybe exactly do it for 2 particles and maybe 3 particles. We're never going to really be able to do a fundamental understanding of what happens when we have a macroscopic number of atoms in a material. And this is not just a qualitative problem. This is a quantitative problem. This is qualitatively impossible. So there's a viewpoint that comes up a lot in condensed matter physics these days is sort of as an emergent approach, where we try and look at the emergent behavior that comes out of the collective interactions of large numbers of particles, so in a condensed matter system. And then so this is the example here is the cow, which you're never going to write down for solving the Schrodinger equation. and yet we can study the organizing principles of the cow, et cetera, and make predictions about how the cow works and that sort of thing. One of the things that comes out of this viewpoint is that, of course, we know that matter is made up of protons, neutrons, and electrons. That's all there is. But in condensed matter systems, we can have many more, a wide range of collective excitations, which we sometimes call quasi-particles. These are the quantized excitations of the system. We're all probably very familiar with phonons, which are the lattice vibrations, and magnons. But there's a whole zoology of these things. There's going through here of things that can appear. There's the rotons in circulating helium-4. There are monopoles, which do not exist in nature, but we can study them in condensed matter systems, for example, as the excitations in spin ice, which is a material that's also people in the BIMR spend a lot of time looking at over time. Another example are the so-called Majorana fermions, which neutrinos may or may not be, but these are particles that are their own antiparticle. So if you bring two of them together, they can annihilate to each other, two identical particles that can annihilate with each other. And these Majorana fermions are also predicted to exist as the excitations in certain exotic superconducting states. So one of the things that we like to do as condensed matter physicists is try to make interesting materials where we can study, where we can get new emergent excitations, and then we can study them in our laboratory, even if they don't exist as free particles in the natural universe. So one of our playgrounds for this sort of thing is in, for example, in quantum spin systems. And the sort of classic example of that is if you have even just a straightforward system with antiferromagnetic spins, the classical ground state, which is the Néel state, which is just alternating spins up and down, is actually not an eigenstate of the Hamiltonian that describes those spins. And so the real ground state can't actually be that particular Néel state. It's not bad as a description in 3 dimensions, but as you go to lower dimensions and to more quantum spins, like spin 1/2, it becomes an increasingly bad approximation. In fact, we know in 1 dimension where we can solve the problem exactly, it doesn't look anything like that at all. So various exotic spin states have been put forward as possible excitations in these systems. And one of these that we're spending a lot of time looking for are so-called quantum spin liquids. And these are systems which would you'd have a highly correlated electron magnetic state, but the state would remain dynamic down to the lowest temperatures. Okay, so that's so the sort of the important driving point behind this is the idea of geometrical frustration. This is a sort of a very, I'm sure, a slide that everybody has seen many times before. In fact, I think we probably saw something like this in Eric Sorensen's talk last week. In geometrical frustration, you have you arrange magnetic moments or spins on a lattice where you cannot satisfy all the pairwise interactions simultaneously. So the idea, the classic example of this is to have antiferromagnetic spins on a triangular lattice. You go up, down, and then the third one doesn't know what to do, and so it's frustrated. You can take this to 3 dimensions. One way you can do it is on for example, a lattice of tetrahedra. Once you make two spins like this, and the other 2 are frustrated. This is a powerful thing to do because essentially you end up with you can have a very large degeneracy in the classical ground states, which can allow then a lot of transitions between equivalent states, which then enhances quantum fluctuations, and you get competing low temperature phases, and it raises the possibility of having new emergent phenomena and new quasi-particles that you might like to look at. So a lot of these frustrated lattices that you see have these triangular motifs, and there's the Pyroclare Lattice, which is something that people study quite a lot around here. We have the Kitaev Lattice shown over here, which we heard about last week in Eric Sorensen's talk. And another one is the so-called Kagome Lattice, which is named after a Japanese basket. It's a sort of a weaving pattern. And it's basically triangles on the corners of triangles. So it's a corner-sharing triangular lattice, like so. And one of the things that makes this a very highly degenerate lattice is that if you have up, and then down on this one's frustrated. But once you make a decision here, even the connectivity to the neighboring triangles is not very strong, because each triangle is only connected through a single triangle. And much like in the Pyroclare Lattice, which is corner-sharing tetrahedra, this weak connectivity allows you to have a very high degeneracy in the ground state. And so this is where people tend to look at these lattices to find exotic behavior. So the classic example, of course, is the Pyroclare Lattice, of which we've probably grown several pounds of this material now up on the 4th floor of this building. It's extremely powerful lattice. You can change the rare earth in this system, and you can actually change the B site as well if you want. But even within that, you have a full zoo of possible systems you can get. You can make the so-called spin ice material, which is dysprosium titanated as an example. And this is a material where the excitations are thought to be some sort of magnetic monopole. And so people are trying to look for them in that system. There's other materials like terbium titanate, where this is a plot of just a spin lattice relaxation rate. And you see that as you get down to low temperatures, it becomes temperature independent. And these fluctuations apparently persist to the lowest possible temperature. Here we're down to about 50 millikelvin. So this is a potential quantum spin liquid, which has been a real holy grail for condensed matter physicists for quite a while. The Kagome lattice is something that's been studied for a long time. In fact, back in 1994, even back when I was a postdoc, we were looking at this in early MUSR experiments. And this is a system which again has a gradual slowing down of the spin fluctuations, and they tend to persist to the lowest possible temperatures. And so this material has been postulated as a possible quantum spin liquid example. However, it turns out that this material is not a perfect Kagome. So though you have a beautiful Kagome lattice, but there's also there turned out to be some magnetic defects in here that can lie on the planes in between the Kagome planes, and that may be resulting in some of the anomalous behavior. So there's been a constant search to try to make better candidate materials which have fewer possible confusing details in them to make them the best possible example. This is a very interesting material, though. It has spin dynamics which slow down. The spins remain dynamic to the lowest temperatures, but the spin dynamics are not understood and how it works. So even if this is a more complicated example, it still raises a lot of questions that actually even now are not yet understood. This is the people in the progression of this. People went to try to make better materials where they had fewer of these interplane defects. And a really beautiful example of this is the mineral which occurs naturally and is known as Herbert smithite, which now of course is grown in the laboratory. And this has been the subject of inelastic neutron scattering studies here, where you see the excitations spread out over very large ranges of Q, which is evidence for what you expect for a spin liquid without actual Bragg peaks due to ordering. Takashi and Mai's group here in the basement of ABB have made a real industry of looking at the spin excitations in these systems and understanding the role of whether or not there's a spin gap in the system, and what the details of how the things like the night shift and the 1/T1 are changing at the lowest temperatures in this material. Of course, the structure of materials is very important for describing their properties. And this has come out very clearly in the last number of years, and people studying the properties of these twisted bilayers and trilayers of graphene. So here you just take a single layer of graphene, which has this nice hexagonal net. And then you can, if you start stacking them together, you get these beautiful moire patterns starting to appear. And you can seemingly create every electronic state of matter you like. And one of them, in fact, is a superconductor that you can see here. Here you see very interestingly, looking at the resistance at different temperatures for a certain twisted pattern. And you see, in fact, you have multiple superconducting states as a function of magnetic field. You can at the lowest temperatures here, you can see you have a superconducting state. Resistive state appears again, and then a second superconductor emerges at that level. And it's thought that one of these states may in fact be an unconventional state where, for example, you have spin triplet pairing rather than the usual spin singlet pairing. And again, this is made up of starting with graphene, which is itself starts off basically as an insulator, but as you stack it together with precise control of the lattice, you can turn it into a metal and a superconductor. Okay. So people have been looking at these frustrated lattices, looking at for interesting electronic and magnetic properties and superconducting properties as well. Of course, in order to have a superconductor, you can't have an insulator. So you have to choose versions of these materials which are metallic instead of superconducting. And this was first done back, sort of most famously done in about the early 2000s, when cadmium rhenium oxide, which has the same pyroclare structure as I was mentioning before, also was found to become superconducting. And for, you can see the resistivity here shows you a nice resistive transition of just above 1 Kelvin. You can see the Meissner effect in the expulsion of magnetic flux at the transition temperature. And you can measure things like the upper critical field, which all good evidence of a bulk superconductor. One of the interesting things about this system, although the superconductivity in many ways looks rather conventional, and I would say this material, is that the state at which the metallic state at which it comes out of, there's a much higher temperature transition, which is up just below room temperature at about 200 Kelvin, which you see in the resistivity and also in things like the susceptibility. And this is thought to be some sort of a charge density wave. And so you're having a superconducting state emerge not just from a sort of a normal, uninteresting metal, but from a sort of a more complicated and more complicated material, certainly. Okay. So there's been some recent effort to, in the last little while, to try to look at Kagome metals, and that's sort of going to be the bulk, the sort of the subject of much of what I'm going to tell you about today. One of the early most interesting examples of this was in the material iron Fe3SN2, which has a sort of a structure here where showing you the irons here on the lattice, and you see the irons form this Kagome pattern. So this material actually becomes a ferromagnet. And so one of the peculiarities about the Kagome lattice is that you get this linear dispersion of the electron energy as a function of wave vector. And normally in a classical metal, you have a quadratic dispersion. So E is 1/2 mv squared, or h bar squared k squared over 2m if you prefer. And so that's a quadratic dispersion. But so this linear dispersion is really quite unusual, and in fact, this is what you expect for the dispersion of photons. And so this is sometimes referred to as a Dirac dispersion, or it's a relativistic sort of dispersion. So it's interesting. People have been spending a lot of effort looking to studying materials with this linear dispersion. These Veil metals and things like that have that kind of linear dispersion in them as well. So in these materials, in the presence of ferromagnetic ordering, you may have just the spin up part of the band occupied, and then when there's some spin orbit coupling of these systems, and these two crossing bands actually repel each other, and you get a small gap opening up there. So these sorts of materials have been studied for, this material was discovered in 2018, so it's quite an interesting topic going forward now. The sort of things that are seen in these materials. First of all, here's some angular resolve photo emission studies of these things, and you can see these linearly dispersing bands through here. In fact, you have sort of two bands crossing right around the right sort of in the near vicinity of the Fermi level. One of the things that's quite interesting about these materials is you see an anomalous Hall effect, which is essentially if you plot the Hall voltage as instead of having it go through 0, as you'd expect in a conventional material, in fact, there's a finite offset of that, and so that's sort of an interesting type of behavior that people are trying to understand in these materials. Okay, so quite recently there's been a lot of interest in finding materials with this kind of structure, and so a group, this is actually a paper by at this point Brendan Ortiz down here was a graduate student working in a material science group, and he cooked up a number of materials which had this Kagome structure. And so this is materials such as potassium, vanadium-3, antimony-5, and then you could change the potassium to any of these going up and down the periodic table. You could change potassium to cesium or to rubidium, and he was able to grow all of them. And so what's interesting about this material is that the vanadium have a Kagome lattice, which you can see here in the red, and in fact, whereas in fact the antimony form this graphite now, which I showed you a picture of earlier on in that moire pattern. So you've got, and this graphite structure also is sort of the building block, if you like, of that Kitaev lattice. So it has a lot of interesting building blocks in this lattice, and so they're stacked up along the c-axis like so, with the potassium reasonably separate or from the Kagome planes. So the center atom spot of the Kagome is occupied, in fact, by an antimony. So there's two different antimony sites in this material. Okay. So here's the overall crystal structure, and there's I think that's I believe that's an STM picture of one of the images. I don't recall for offhand, in fact. So they've done, you can do DFT calculations of these materials, and there's a little bit of uncertainty about where the Fermi level will be, but you can do the calculations for each of them, and of course they're quite similar as you'd expect. But there's lots of interesting features in them. You can see these, you have these band crossings, these linearly dispersing bands, so you seem to have these, DFT indicates that these materials are metallic. So for that matter, so does experiment. And you see these Dirac points where these bands are crossing near the Fermi level, which also brings up the idea of there could be some interesting physics here. So these materials were discovered in 2019, and then there were some quick characterization of them indicated that, in fact, they shortly after that there's an awful lot of interesting behavior happening in these materials. So the first thing you see upon cooling it down from room temperature, if you measure the resistance or the susceptibility or the specific heat, is there's a very clear phase transition at 94 Kelvin. You see it in all three techniques. And when you go ahead and then do a scattering experiment, you see that you in addition to the regular Bragg peaks that you had indicating your crystal structure, some superlattice peaks appear as well, which tells you that you've got some sort of a charge density wave forming in the material. So there's a lowering of the symmetry at this point. So there's a charge density wave at about 94 Kelvin in this material, which shows up in all these bulk measurements. But then, interestingly enough, if you cool down to even lower temperatures, and what you find is that you end up with a superconductor as well. So if you see, here's the resistivity, you see you go from a finite resistance state down to a zero resistance state at around 2.5 Kelvin. You see that in the magnetic susceptibility, where you get full flux expulsion as well, indicating a bulk superconductor. And you also see a sharp lambda-like anomaly in the specific heat, which you can, of course, then depress with a magnetic field as you move through the critical fields. So this material has, again, you have a superconducting state, which then emerges out of a metallic system, which has a charge density wave in it as well. They followed on with this. They found that, of course, then they already had made materials. You can change the cesium into potassium, and you also you end up with a superconductor as well, with a slightly lower charge density wave transition temperature. If you squint hard in the resistance, you can see a little kink there, and same with the specific heat, you can see a little feature there. You see a bulk superconducting transition in this material at around 1 Kelvin, which you see in resistance, specific heat, and magnetic susceptibility. Another group, people jumped onto this fairly quickly. A group in China managed to make the rubidium version of this material in single crystal form. You can see there you see some of these crystals here. They're grown by a flux method. You see beautiful scattering patterns there. Again, you see a jump in this charge density wave opens up about 103 Kelvin again in this material. You see it in the susceptibility as well. You see about a 1 Kelvin superconducting transition, a little bit broad in the resistance of this sample here. But it's certainly a bulk superconductor. These materials are very clean, so they're very good metals, in fact. And so here you can see Shubnikov-de Haas oscillations, which tell you that you really are dealing with fermions in there, and you can measure, and the samples must be extremely clean for you to see these coherent quantum oscillations. And so from that, you can see things about some of the parts of the Fermi surface and the extremal Fermi surface orbits, and you can get things like the effective mass from the temperature dependence of these orbits. So they're very nice materials. You can grow them in very, very clean form, and there's a range of superconductors that you can study. Okay, so my group here uses a technique called muon spin rotation, which is a way of characterizing the magnetic and electronic properties of materials. So I should spend a few minutes telling you about how we do this. We first of all, of course, have to do mu-SR. You need to have muons. So we make these at a particle accelerator, which start when we typically use Triumph in Vancouver. You start off with a 500 MeV proton beam, which hits a low Z target like carbon and beryllium. And one of the things you make in that reaction are pions. You make a lot of other things, but some of the things you make are pions. So pions, the pi plus is a quark anti-quark pair. It's an unstable particle, and it will decay by the weak interaction. And it decays the pi plus will decay into a mu plus, a positive muon, which is essentially a heavy positron, and a muon neutrino. And this is with about a 26 nanosecond lifetime. So this is fairly quick. So if we take a pion, which is at rest, for example, on the surface of our production target, when it decays, the muon and the neutrino have to go in opposite directions to conserve linear momentum because the pion was at rest. The pion has spin 0, so there's no angular momentum beforehand, so there can't be any angular momentum afterwards. Neutrinos, because this is a weak decay, are made 100% spin polarized with their spins anti-parallel to their momentum. So there's only left-handed neutrinos in the universe. So this was what was predicted by T.D. Lee and demonstrated to be true by Madame Wu in some very famous beta decay experiments back in the late 50s. Okay, so once you have this, you have a muon, and the muon itself is an unstable particle, and it will decay again by the weak interaction into a positron, which is just a positively charged electron, and then two neutrinos. Okay, so there's an anti-muon neutrino and an electron neutrino, and this is about a 2 microsecond lifetime. Now this is also a weak decay, so and the way this is manifest is that the positron is given off preferentially in the direction of the muon spin at the time of decay. So if we know which way our muon, when we make our muon, we know our muon spin is pointing anti-parallel to its momentum. When it decays, we have a good idea of the direction of the spin, direction at the time of the decay, and from that's how the basis of our MUSR technique. So the experiment works, a muon comes in, it goes through a detector and starts a clock, lands in our sample. The spin then precesses under Larmor precession in the local magnetic field until it decays at some time 2 microseconds later on average. And when it decays, the positron goes through another plastic scintillator detector, and we stop the clock at that point, and we make a histogram of detected positrons in some direction as a function of time after implantation. So we do this one muon at a time, and then we build up a spectrum, a decay spectrum like this, which has, of course, the muon lifetime on top of it. But then this lifetime curve is superimposed on that, the projection of the spin on that axis. So if the muon happens to be pointing towards the detector when it decays, the positron is more likely to go in that direction than the opposite direction. And once we do this many millions of times, we have a nice curve that looks like so. And from that, I'll show you a better picture in a minute. Then from that, we can extract things about the muon, the spin polarization function. So these experiments, you need to have an accelerator. So here's an aerial schematic drawing of TRIUMPH. So here's the main accelerator is in the middle there. It's the world's largest proton, or it's actually a hydrogen minus accelerator. It's about 200 feet in diameter. Then the protons are extracted down this beam line here, where they hit a series of production targets, imaginatively called T1 and T2. And there we make muons, which are then fed into the secondary channels away from the target. There's a sort of a picture of what it really looks like. You have a big pile of concrete shielding, which keeps the radiation away from landing on people and making it safe. There's a prime minister standing there, making sure that everybody's working hard. There's the former director of TRIUMPH, who's now the head of the American Physical Society, thanking the prime minister for giving him some money. Here's the beamline 1A, comes down underneath this pile of shielding. These are about the size of shipping containers. They're about 50, 60 tons a piece. And they cover the beamlines and the production targets, which are under here. And at the very end here, you can see 2 muon beamlines coming out at the end. You can see some quadrupole magnets, which are used for focusing the beam, and the spectrometer would land on the end here. So this is about 4 feet off the ground, just to give you the scale. If you look carefully down there, there's a distorted looking person. So it's it's about the size of going to like a spallation neutron source or a synchrotron in Saskatoon. It's a large facility, hundreds of people working inside the fence any particular day. So we can do experiments there on condensed matter systems, just to show you the sort of things we can use. Here is a sample holder that goes inside our dilution refrigerator, which you can see over here. There's a former graduate student who's now a scientist at a national lab in the States. But we end up with all this equipment, and there's a little sample sitting on the end of a sample holder. So that's a silver sample holder, which holds, we attach our sample onto for thermal conduction. And there, it's about, as you can see, it's about half a centimeter on a side. So we can go down to experiments as low as 20 millikelvin and fields up to about 5 Tesla. We can go to very high fields, so we can go into about a 7.5 Tesla magnetic field, where the muons will precess at a gigahertz, which is about our timing resolution, which we have to then time all of our events down to about 100 picoseconds. We can also do experiments under high pressure by using high energy muons, where we can go into things like pressure cells and do that kind of experiment as well. So here's an actual decay curve. This is just showing muons that have been implanted probably into a piece of copper or something like that, with about a 60 Gauss magnetic field applied to it. And you see us on top of the muon decay curve, you see an oscillation of the polarization as the muons spins precess pointing either towards the detector when they decay or away from the detector when they decay. Of course, we know the muon lifetime very well. It's 2.2 microseconds, so we can divide that out, or we can just take what we normally do is we take opposing sets of counters, because of course if the spin is pointing towards this particular counter when it decays, it'll be pointing away from that one. So the signals will be exactly 180 degrees out of phase. And then we can take what we call an asymmetry, which is just plotting the difference in the count rates divided by their sum, and the muon lifetime disappears, and we just measure the spin polarization function. Because we get our spins are polarized by nuclear physics, we don't need to do like they do in magnetic resonance and apply a large magnetic field to generate a polarization. So one of the advantages of MUSR is we can do the experiment in zero magnetic field, which allows us to then study the intrinsic behavior and not even if the field might change the sample in some way. So we can, for example, it's a volume sensitive probe. If we have a material, here's an oxide, calcium vanadium oxide, and this is measured in zero magnetic field, and we see beautiful precession of the muon spin polarization. And that's because this material is an antiferromagnet, and by measuring the temperature dependence of the precession frequencies in this particular material, there are 2 sites for the muon, so there's 2 frequencies. Here I'm showing you the temperature dependence of one of these frequencies, and that's just an order parameter for the magnetic order. It would correspond to the square root of a Bragg peak intensity in neutron scattering. But because we're not a diffraction technique, we implant the muons and they stay at rest. We don't need to have long range order to see the sense of internal magnetic fields ordering. So for example, in materials which are glassy, we get a characteristic relaxation function, and you can study glassy behavior just as well as long range ordered materials. So sometimes that part of it can be more powerful than a diffraction scattering experiment. Of course, we lose information about correlation lengths, so nothing ever comes for free. So talking about superconductors, which is what we're moving on to, I use the word unconventional superconductor sometime. And so to differentiate what I mean, we'll say a conventional superconductor is one where the gap function, which describes the pairing state between the 2 electrons in a Cooper pair, if that gap function, which depends typically on momentum, if it has the same symmetry as the crystal, typically then we'll say that's conventional. And usually we take this gap function just to be, in fact, just a constant, and so that's our so-called S-wave pairing. An unconventional superconductor might be something like the cuprates, where this gap function has a lower symmetry, and in fact, in the cuprates we have a so-called D-wave pairing state, where the gap actually changes sign at different places as you go around the Fermi surface, and actually has places where it identically goes to 0 because the gap crosses there. So that an unconventional superconductor is one where the gap has a lower symmetry than the crystal structure that it's living in. So in addition to this lack of rotational symmetry here, there are other broken symmetries as well, and one of the most common ones that we spend a lot of time looking at is broken time reversal symmetry, which is in some sense fancy talk for an internal magnetic field being generated. Okay. So once we have a type 2 superconductor, which is most interesting materials are, one of the things we can look at is the so-called vortex state. So if in that situation, if we apply a magnetic field, the field penetrates the superconductor in the form of vortices, which repel each other, and so they form a lattice. Now the lattice constant is given by the strength of the magnetic field, because each vortex carries 1 quantum of magnetic flux, and so you can calculate the density of vortices by just knowing the applied field. So here's an STM picture showing you the density of states as you tunnel into different directions. However, around each vortex, which is essentially a normal tube, you have a supercurrent flowing around that, which then screens the magnetic fields out of the bulk. And these supercurrents then die off as you go away from the vortex on a length scale given by the London penetration depth, which is how magnetic fields screen out of at the boundary between a superconductor and a normal material. So there's three length scales in a superconductor in the vortex state. There's the lattice constant for the magnetic order, which is determined by the magnetic field you applied. There's a length scale over which the superconducting wave function varies, which is essentially the vortex size, or the separation on average between two electrons in a Cooper pair. That's the coherence length. And then there's the magnetic field penetration depth, which is how magnetic fields are screened away from a normal material. And that's the penetration depth. In MuSR, we implant muons who land randomly throughout the vortex lattice. And so they experience the magnetic field in different regions, and they sample the whole field distribution. So if we Fourier transform our precession signal, of course, the muons land near a vortex core, they see a large field and they precess quickly. If they're well away from the vortex core, they see a smaller field, and so they precess more slowly. And so they dephase, and this gives a damping of the polarization. If we Fourier transform this signal, what you see there's a minimum field that occurs, for example, in the center of the triangular lattice, farthest away from the vortices. There's a maximum field, which is at the vortex core, which gives you a high field cutoff. And there's sort of a most likely field, which is this along this boundary in here. And so from that, you get a classic line shape. And from that, you can actually directly determine you can measure the penetration depth and the coherence length directly. If the vortex lattice is a bit disordered, then maybe you can't do that, but in quite as much detail. But the overall line width, which is the width of the field distribution, is essentially given by the magnetic field penetration depth, which depends on essentially the superfluid density divided by the effective mass. So in a superconductor, if you can measure the broadening of this precession signal, you directly measure the superfluid density, ns over m star, and then you can measure its temperature and field dependence. If you do it so here's something in more detail, you can determine things like the vortex lattice geometry. If you have a well-defined lattice, you can really see all of these details and measure directly the coherence length and the penetration depth, etc., and determine the geometry. So we've done this, for example, looking at iron arsenic superconductors. We can see as you change some of the doping, we're looking at the temperature dependence of the superfluid density here, which is 1 over the penetration depth squared. You see its temperature dependence changes from being quite flat at low temperature to coming in with much more of a slope. And this is associated with a change in the pairing symmetry with doping in this material. We've looking at, here's another interesting new material that we've recently looked at, where you see again, measuring the temperature dependence of this broadening or this relaxation as a function of temperature, and then fitting its temperature dependence, you can actually see that these materials have two gaps, both of which have S-wave symmetry, and you can get fairly precise measurements of these by fitting them to theory. Okay. So we've done a measurement we've done a series of measurements now on cesium, vanadium 3, antimony 5. So here's a picture of our sample holder that's about 1 centimeter wide, and here you see a series of crystals that have been glued to the silver sample holder. So this whole square centimeter of sample is loaded on top of a dilution refrigerator by a bunch of graduate students and scientists up here. Actually, this was an undergraduate at the time. So here's the dilution refrigerator. So it goes from being at room temperature to being at 100 millikelvin in about 2 hours. And this is important because the beam is on and the taxpayers are paying for us to be there. So we want to be quick about it. So the first thing we did in this material is we were looking at we did measurements in a transverse magnetic field to measure the relaxation rate. So here we are above TC, you see very weak relaxation. This would just be due to the nuclear dipole moments of the material in the system. And then as we go into the superconducting state, we set up a vortex lattice, which makes the field distribution less homogeneous. And so we have a damping of the relaxation. So we fit this to extract the damping rate. Of course, there's a slight negative frequency shift due to the Meissner effect, which tends to lower the average internal field. But in this geometry with a large demagnetizing effect, that's not a very large effect. And now we can look at the temperature dependence of the damping rate of this signal and learn about the pairing state. So here we are. So here the data points here are the relaxation rate as a function of temperature. You can see here's TC of about 2.5 Kelvin. So these are the data points, and then we can fit the temperature dependence of this to various models. The first thing we see is that if we try to fit this to just a standard weak coupled BCS temperature dependence, it doesn't work. So what we use is we use a more general form. So from BCS theory, we know what the temperature dependence of the gap is in terms of the reduced temperature T over TC here. This is just as a result of BCS theory. We know in the clean limit, we can then calculate what the superfluid density is. It depends on basically states that have been excited over the gap. So here's the Fermi function, and so it's we need basically the derivative of the Fermi function with respect to with energy. We integrate this over all energies. This is basically part of the gap, looking like the gap equation in BCS theory, and from that we can actually determine. We assume for now that a BCS form for the gap, and we can measure what the gap would look like. And so here's the best fit that we get for that, shown in the blue here, and we get a gap at 0, which is turns out to be about a third of an MeV, and this is significantly less than the BCS value of 0.4 millielectron volts for the TC of 2.5. So the fact, that in weak coupling BCS theory, you get superconducting for an arbitrarily weak interaction. And so you can't have a smaller gap than the BCS gap, because that's the weakest one that comes out of the theory. If you have a stronger interaction, you can get gaps that are bigger, but you can't get a smaller one. So the fact that we get a significantly smaller gap tells us that we either have to have multiple gaps, which is possible because you have different parts of the Fermi surface. You may have superconducting pairing on one part of the Fermi surface, which is the sort of the driving things, and then there can be a proximity effect in basically in reciprocal space, inducing superconductivity on other bands, and they will have a significantly weaker gap because the superconductivity is not fundamentally residing there. And so what we're in the process of doing now is doing the fits and fitting. It's most likely that you see that there's a temperature dependence coming in at low temperature here, which is not there in the BCS state, which should be flat. So we're now extending our analysis to look at this, to have an S wave gap for the primary gap, and adding in a second D wave gap, which will be the leading term on that. So right now it looks like we have multi-gap superconductivity, much like we do, for example, in magnesium diboride, and that one of the gaps may in fact be a non-S wave. One of the other symmetries we can look for is so-called broken time reversal symmetry. In the case of strontium ruthenate, which is a very famous example of this, we have a gap function which can be either a Kx plus IKY state or Kx minus IKY state. And when you have boundaries, just like you have boundaries between different regions in a ferromagnet, where the order parameter direction, spins order, you'll have one domain where the spins are pointing in one direction, another domain they'll be in another direction. You have a domain wall between those. So if you have a domain wall between two phases of the superconductor, if you have a phase that changes with distance, that rotating phase requires a current. And so you get a Josephson current, which flows along the boundary between the different domains. And those physical currents will make a real physical magnetic field, which you can then detect. So we've done this in strontium ruthenate. Here you see the relaxation rating above TC is small due to the nuclear dipole fields, and you see a relaxation which turns on below TC. You can see that there, and that shows you that your superconductor has broken time reversal symmetry. This has been seen in a number of superconductors. We've seen it ourselves in the case of uranium platinum 3, which is a heavy fermion superconductor. Other groups have seen it in, for example, in these clathrates like praseodymium, osmium 4, antimony 12. And it's not just seen with muons. There are now experiments using a Kerr rotation group out of Aaron Kopitolnik at Stanford. Only 20 or so years after us managed to observe the same thing in uranium platinum 3. So it's not just a muon technique. You can see these broken time reversal symmetry states with other techniques as well. So the bottom line in cesium, vanadium 3 antimony is that in fact there is no broken time reversal symmetry. The spectra at 20 millikelvin at our base temperature and 2.8 Kelvin are exactly the same. And so within the evidence, within the degree of which we know how small our fields are, which is about a third of a Gauss, we can say there is no evidence for broken time reversal symmetry in this system. So we don't break that symmetry in this material. The next thing we did in this experiment is to look at what happens if you move the Fermi level around. So it turns out that you can take cesium, vanadium 3, antimony 5, and you can change some of the antimony into tin. And this essentially is a way of, you're basically hole doping the material. and you can change its properties quite a lot. So here's showing you, for example, the magnetic susceptibility. First of all, for fairly low amounts of doping, that even 3% doping actually causes the TC to rise rather dramatically from about 2 Kelvin to more like 3 Kelvin. So that's a 50% increase in TC with just 3% substitution. And then as you further dope it up, you could eventually, you go through a dome in maximum in TC, then you go down to a minimum, and then a second dome appears. Somewhat reminiscent of what a picture I showed you of the triple layer graphene as well, where you had an emergent superconductivity which appeared, then went away, and then appeared again. Here it's as a function of doping rather than as a function of applied magnetic field. But the second thing you see is this charge density wave that was there, that was seen very clearly in this, for example, in the susceptibility. Here we're plotting the derivative of the susceptibility with respect to temperature. That CDW temperature drops dramatically, and by the time you get over here, you have no CDW anymore that's discernible. So we started to look at these materials to see how we still have a bulk superconductor. You see very good flux expulsion. It's still 100% for all of these samples, and to see how the nature of the superconducting state is going across the phase diagram. So we took a series of three dope samples. One with about 3%, where you've reduced the ordering temperature of the CDW significantly, and you've raised TC though up from about 2 Kelvin to somewhat more closer to 3 Kelvin. So we're actually, the onset temperature here is, you see, is about 3 Kelvin. And then we looked at a sample right at the minimum and a doping of 0.1 with the lowest TC in the series. And then we went at a third sample that was up near the maximum, and we want to look at each one of these. So the first thing you see is in the 3% dope sample, the vertical axis, these are all plotted on the same scale. The superfluid density is the highest here. And so as we're doping, we're lowering the superfluid density. And so we're actually adding holes is getting rid of net charge carriers in the system, whereas we're moving the Fermi level around. And so in fact, the carrier concentration is changing quite strongly. You see here, you have very strong temperature dependence again to this superfluid density. There's a small slope at low temperatures, and it's changing strongly over a wide temperature range. And this is very much changing much more. The slope changes over a much wider temperature range than in BCS theory. For here we have the most highly doped sample, and here I'm showing you basically that fitted temperature dependence of the superfluid density is what you expect from BCS weak coupling, and the sample in between them is somewhat intermediate between the two. So we go from something looking very, very different, very multi-gap at the lower doping, just like it was in the pure material, and becomes much more single gap like as we move up to the highest dope sample. So in some sense, the superconducting state, it looks like it's becoming simpler as we move off into this high dope state. We've looked for, just for completeness, we've looked for broken time reversal symmetry in all of these samples. One possibility here, of course, is that you have these different domes of superconductivity. There's nothing to say that the superconducting state out here has to be anywhere near the same superconducting state as over here. There are systems where you go from being an S-wave superconductor and you change some parameter and you go into a D-wave or a P-wave superconductor. We see that we move into we start off with a multi-gap system and we end up with a pure S-wave BCS-like superconductor over here. And none of these superconductors have broken time reversal symmetry associated with the superconducting state. Okay. I see we're getting close on time. We do see some magnetism in these materials, which we're still trying to sort out. So I'm sort of putting this near the end. So here's the susceptibility of one of our single crystals, for example. And so as you cool down, so this is comparing both field cooled measurements in the red and zero field cooled measurements in the blue. And you see mostly that these measurements are exactly the same. And here's the charge density wave transition at 94 Kelvin. They're exactly the same. But if you look below 50 Kelvin, actually you start to develop irreversibility down here, that the susceptibility matters on how you got there. So there's something magnetic happening in the sample. We've looked at but it's not happening, it's not associated with the charge density wave transition. If we look at if we plot the normalized difference between the field cooled and the zero field cooled, so we just take the difference between the two of them and divide by their sum, you see above about 50 Kelvin, that the two, it doesn't matter how you get there, the difference is 0. And then below about 50 Kelvin, for all the different doping levels of our samples, we start to see the emergence of this history dependence in the susceptibility of those lower temperatures. And of course, down here at TC, everything goes haywire, but that's fine. So we're seeing some magnetic behavior occurring in here, but it's occurring, so there's a spontaneous change in the internal magnetic environment, which is fairly weak, but non-zero, occurring in bulk measurements of the material at lowest temperatures. We went and looked back at some very careful Miosar date measurements as well. In fact, so the measurements of the superconductor are all done below about, to the left of about 5 Kelvin, so just as low as temperatures. But what we see, in fact, is we see that there's a change in the relaxation rates, which tells us about the field distribution that the muons are detecting as well, also happening around this 50 Kelvin point. So there is a change, there is some magnetic behavior happening in this material. It's extremely weak. These fields are, we're looking at perturbations on essentially the fields of the strength of the nuclear dipole interaction. So we don't yet understand the origin of these things, but there is some weak, in some sense, weak time reversal symmetry changing associated with the normal state of these materials. And that's something that we're now still trying to understand. I see I should wind up because I see our time is running short. Let me just last sort of thing just to say what we're doing now. So those measurements were done on materials made by our collaborators at the University of California. We started a project now up in the Center for Crystal Growth on the 4th floor to look for new Kagome metals. And one of the ones we've come up with is yttrium chromium 6 germanium 6. And this material, everything is nominally non-magnetic. And there's although the susceptibility is non-zero, it corresponds to a very weak magnetic moment of less than 0.2 Bohr magneton per unit cell. There have been other materials that people have looked at in the series where the yttrium is turned into, for example, holmium or some other rare earth, and they become very magnetic. In this material, the chromium is lying on the Kagome lattice. The yttrium and the rare earths are on a triangular lattice. So to look at the real Kagome properties, you certainly want to have a non-magnetic ion there, we think. So here's you can see the 12-fold symmetry in the Laue pattern here. And what we've just started managing to grow these materials in single crystal form. They are metals. If you put a voltmeter on them, you just get a resistance, so they're metallic. And the magnetic susceptibility is actually, although it looks big on the scale, it's because we're very sensitive. But interestingly enough, we start to see some irreversibility of the susceptibility below 1 Kelvin. So we're measuring this down to helium-3 temperatures. So there's some very weak magnetic behavior that seems to be coming into place down here. We haven't seen any signs of superconductivity in this material yet, but this may be a place to start looking as well. So this is part of a fourth-year thesis student project of a physics student, and also working with 2 of my graduate students on this project. So I think I will before I give my final conclusions, let me just make sure I thank people. So this work is a lot of this work is part of the master's project of Jonah Gotro, who's been working very closely with one of my senior graduate students, Sudarshan Sharma. James and Matthew. James has now just completed his PhD, is now doing a postdoc with Pat, in fact. And then Matthew, another PhD student, working on some related projects, and then our undergraduate student. Of course, this collaboration, very important, working with Stephen Wilson and his postdoc and graduate students at the University of California in Santa Barbara, who made the metals I was mostly telling you about. Tomo Uemura is my longtime collaborator at Columbia University, who's been involved in these measurements, and of course, the local staff at Triumph, where we do the experiments. Many of these were done under COVID protocols, so we couldn't have as many people there as we liked as possible. Of course, somebody paid the bills, and so we should thank them. And so just to conclude, where we are right now, this is very much a work in progress. All of this work is unpublished. So we'll hopefully be completing the manuscript shortly. We've discovered that this material is a multi-gap superconductor, possibly with changes in the gap symmetry as we change the doping in it. We don't see any evidence for broken time reversal symmetry associated with superconductivity, although we do see some magnetic environment changes in the normal state. We see that when we hold up the system, we reduce the superfluid density and we move it towards a much more simple BCS-like gap system. Finally, more generally, I think these Kagome and other crystal structures have the potential for hosting unconventional states. And I think the fun part about our job is to go identify these and to characterize them and to search for new ones. So with that, I'll thank you for your attention and be happy to answer any questions.
Okay, that's great. Thank you very much, Graeme. The floor is open to questions. You should be able to now unmute yourself and also to start video, I think. And we're happy to take any questions. Eric, please go ahead.
Yeah, hi Graeme, nice talk. I was just for the yttrium compound that you mentioned at the end.
Yep.
So you haven't seen any signs of superconductivity yet, is that right?
Yeah, well, so we haven't measured the resistance yet, but obviously the susceptibility is clearly non-super. It does not look to be superconducting down to about 500 millikelvin, but at least because we see a we see no, I should point out this is measured in a fairly large magnetic field. So it is possible. This is, I think, measured in a 1 Tesla, perhaps a 1 Tesla magnetic field. So in principle, we could have superconductivity with a critical field lower than that. This is very recent data. So we're basically still looking to see what's in there. My guess is it's probably not going to be superconducting, but because most things aren't. But
okay. Can you dope it?
Well, we've only just grown this. So the question is, if you I think, I mean, I'm sure we can dope, but I mean, you could do things. For example, you could change. You could substitute on the germanium site and put it in something with more charge carriers or fewer charge carriers. You could go one to the right or one to the left in the periodic table and hope to dope it that way. I think and you can also make there's sort of a family of these compounds. I mean that have been made. You can change the chromium into other things as well, and you maybe something. There's not a lot of magnetic moment in here, but there's about 0.2 of a Bohr magneton per chromium on average. So it's a question of, do you want to make something less magnetic? So far we're really just trying to grow the material first of all, and see what its properties are before we go from there. The sort of things we'll probably first do is to measure electric resistivity and do Hall effect measurements as well to see what we can see about that, just to see what the nature of the charge carriers is.
But it looks like very good Kagome planes. Or...
Yes, yeah, no, they look they're very pretty. I mean, you can see the nice 120 degrees, the nice 120 degree angles there. And of course, this is sort of a messy look, very first Laue picture, and probably not the cleanest surface, but yeah, they look very nice, and I think they'll probably, I don't know if they'll cleave or not, but usually you discover if they cleave by dropping them. Or taking a razor blade to them. We haven't done that yet.
Thanks.
Sure.
Okay, Jan, please go ahead.
I have also a question about this compound. Do you know what the bonding states are made of? Which elements contribute to the bonding and antibonding at the Fermi level?
Well, I mean, I view this material as sort of as a metal. So I think it's sort of how I'm not thinking. I think of it as I'm not sure I would quite think of it that way. I would think of it more of an itinerant nature, because I think the chromium wave functions are very spread out here in this material. So I'm not sure I would. I mean, we know where all the atoms are. So I guess that's not. So I guess we know the arrangements of the ions, and so in some sense that's a no. The answer to your question is probably no. That's not sort of the way I tend to think about it, though.
Okay, because sometimes when I look at this kind of Kagome or magnetic versus non-magnetic lattice, they have kind of antibonding states of certain elements below the Fermi level, which is kind of interesting to see which actually contribute to it. So which helps a lot also for the doping study later on to figure out which contributes or which are very close to your Fermi level, and so which are easier to change, because sometimes, I'm not sure about your chromium, but these might be very localized states or very strongly localized states. And so I'm kind of worried that these are more localized than are not very fluent over the entire band or over the Fermi level, that they sit a little bit deeper in the valence band than at the Fermi level.
Well, yeah, I mean, I guess that may be possible. That's something we're going to have to determine, I guess, to see just what, once we, I think people are doing DFT calculations on these materials already, knowing to figure out what the nature of the states are. So far we've been concentrating on just trying to figure out if we can actually make it.
Okay, sounds good. Thank you.
Any other questions? Okay, I don't see any more questions, and the time is coming to an end. So please join me in thanking Graeme one more time for a great talk, and I hope to see many of you back next week for the final installment of the Quantum Materials series. All right, have a good weekend, everyone, and thanks again, Graeme.
Pleasure. Nice to see you all virtually, and see you soon, I hope.